loss calculation, and I think, with my initial matrix numbers, I got a wrong answer, but the wrong was so wrong, oh my God, I need to go back and change my matrix numbers. So it's called backpropagation, where you compute the loss and then go back and update your numbers. So I'm actually trying to make it as non-NLP as possible so that it's easy to understand. So you're actually having that weights which are getting modified. For the same, if you're using the same LSTM to take the inputs and eventually start even outputting, people felt it was not as accurate. So they felt it was more accurate to use two different RNNs, where don't care for the weights of the encoder. Once it's done, just I want only your hidden state. And I have a new RNN with a new initialized set of weights. I'm going to use that to start making predictions, and hence, it becomes more intelligent in the process.
So in general, what's the ratio of the size of the context vector to the word vector? Is y1, if y1 is a vector of size n, is the context vector exponentially larger, or other way around?
The question is, I'm trying to understand the question too. The word vector dimensionality and the context vector dimensionality, are they comparable? Is that your question?
Well, which one stores, you'd imagine that the context vector would be larger because it stores more information. You'd imagine that the context vector would be larger because it stores more information. So I'm asking, is it usually is the hidden state larger, or is the output word vector larger usually?
Okay. So you're actually confusing between two different concepts. A word vector is a vector that just represents a single word. There are multiple ways of creating a word. I'll actually, I think a couple of slides later, I'll be talking about how to create word vectors, the different types of word vectors. So a word vector captures the essence of just that word. Whereas a context vector, context vector, hidden state, interchangeably used, the hidden state is an understanding of all the inputs that have come in. You can decide what the dimensionality of your word vector can be, and you can also decide what should be the dimensions of your model too, which is in this case the RNN. And higher the dimensions and the deep, how many layers of network you have, all of those hyperparameters you can do a permutation combination to understand which ones work better, but conceptually, word vector is just representing just that particular word. And the word vector, let's say I'm going to the movie. The word I am going to the movies, all of these words can be represented by different vectors, all will have the same dimensionality. Let's say if you want a dimensional of 200 dimensions vector, you will create a vector for I which is 200 dimensions, but it's a unique number compared to am, compared to going to. But the hidden state is a matrix which is a different dimensionality, which you can decide what you want it to be. It's a matrix, and it's constantly getting updated based on the loss and backpropagation and stuff. So that's what I think I understood from your question. They're not comparable. But if you can hold on to the question about word vectors, I'll come to the word vectors, and maybe if you still have the question, we can talk about that. Yes, sir.
So the completeness or richness of your training set.
The question is, how do you know the quality of a data set is really of good quality? Sometimes you have a bad data set, and hence, yeah, you could be training on a bad data set. Yeah, that's the question, right? Yeah. That is a major question, and if you remember correctly, I mentioned earlier in your project, if you do any ML project, 20% is only what you do in developing a model, 80% is just making a pre-processing and making sure the data is accurate. One of the biggest problems today is actually lack of good quality data. And when I say lack of good quality data is sometimes the data is missing, inaccurate, incomplete, erroneous, in different format, different units. There's so many problems in our data, and especially in companies like, let's say, IBM or Apple or Google. The data is stored in so many different data sets and different locations, different databases, different formats, and putting the data together and trying to make sense is a bigger problem. That's number one. Number two, when you're doing an image processing or a language translation or any of such problems, having human-created data sets is so difficult, so expensive. Some universities have invested, some companies have invested money to hire people to create data sets, but there are not enough data sets available. So, for example, in image processing, there's something called MNIST or CFAR10. There's some data sets available, but that's the same data sets being used by every company or every research project to check how good the model is, but there's no other type of data sets available. There are companies which are available, so that's another good idea. If you want to start a company and want to make a lot of money, instead of doing ML projects, try to do data creation, data set creation. There's a lot of companies making huge amount of money on creating data sets. Yes, sir.
I'm not worried about the quality of data. Assume you have perfect quality. I'm worried about structurally. So when you want to train your model, you know you see what I mean?
Yeah,
so,
yeah.
So whether you initially give it in individual words, then more complicated sentences, et cetera, to help it train or learn better or be trained better.
When you say complicated sentence, I think I don't understand, but right now the data sets are, no, it's okay. Data sets, I think they are having different types of inputs. Let's say if you're trying to do, let me take an example of language translation. There's certain corpora available for English to French, English to German translations. When they do that, what they do is they actually pick random sentences from different sources of books and papers and online stuff, and then identify human beings who actually can translate those sentences into a foreign language, whatever language it is. And when they pick the sentences, they do pick different types of sentences, different structure, different complexity, different length, different unknown words or difficult words and all of that stuff. Yeah, they do. But that's where, when I say quality of data set, that's what I meant. It could be incomplete, not appropriate, erroneous, not complicated, it does not reflect the real world. There could be so many situations, but that's where the whole problem is. Getting the good quality data set is a problem. No, I don't think so. Right now, just the fact that a lot of research companies are using the data set for running their models itself could be a sign that, okay, this could be a good quality data set. The fact that it has missing data, incomplete data, erroneous information also goes a long way in having a more generalized model, because you can't have a perfect real life situation and data set all the time. So sometimes it's data, erroneous, missing data is fine. The measures to see whether the model is doing fine or not, especially in textual context. Let's say if you have a translation model and it does a translation. Let's say I create a machine translation from English to French and you create another model which is doing English to French. How do you know my model is doing a better job than your model? Because every sentence is different, every paragraph you're translating is different. So there are some metrics called BLEU scores, BLEU scores. And there's another score called ROUGE, R-O-U-G-E scores. One shows the precision, one shows the recall numbers, but mathematically it's difficult to compute how my translation is better than your translation, because you can translate a sentence in another language in different ways, and hence it's an NLP. That's a big problem. It's an issue. I'm checking my time just to make sure I do cover. Yes.
Hello. Whenever you have some time during this training, could you please give us some best practices about is there any best practice for handling missing data, or like specific, like data cleaning specific to NLP domain? I mean, not immediately, but whenever you think you can plug it in, I think that's something we are having a lot of trouble on that.
Okay. I'll try to say a few things, but again, what can be used to clean up data is more of specific about what the data is and what the purpose is, what type of objective you're trying to solve. So it's going to be a little more case sensitive, but I'll try to see if I can. Okay, coming back to the encoder and decoder, I just want to show you one more time. So hidden state is mentioned as ht is a function of xt, which is the, so hidden state at time step t is a function of the input at time step t and the previous hidden state. So every time a new hidden state gets created based on the previous hidden state and the current input. And you have an output vector, which is sometimes the context vector, which is actually a function of all the hidden states. This is where I think goes back to your question. Sorry, the gentleman sitting there in the front. Yeah, goes back to the, in the context vector, see here, if you're actually using all the hidden states instead of just taking the last hidden state, some experiments have taken the last hidden state and thinking that it's going to be, it captures all the information. Some other experiments have taken all the hidden states at every time step and did do a function on it and then convert, have a new hidden state which is being used. It is called context vector, but that's a different experiment, different experiments people have done. But mathematically, that's why you show in an encoder. Let's show decoder from here. You guys, I think, may enjoy the decoder here. The probability of y1 to yt at time step t is dependent on all the previous outputs and the context vector, which can be shown as the probability of yt at any point of time t is dependent on the previous output, the hidden state of decoder at time step t, and the static hidden state or the context vector of the encoder. Now comes the situation where you have the input context vector of the encoder coming in, and you also have the hidden state of the decoder at every time step, and the previous word which is output are all factors that go into predicting the next output. Okay, so instead of just only sticking to the hidden state of encoder, now I'm using too many words, I want you to please listen to this. Instead of focusing on the hidden state of encoder at one time, as I showed in the previous slide, there are some models which say instead of just focusing only one time, can I go back and look at what was the hidden state of the encoder at every time step. So I want to know, tell me once again what the hidden state was. Tell me once again at every time I'm outputting. So this is called encoder-decoder with a peek. So it's actually taking a peek at what was the hidden state of encoder. That's another variation which has come. So you have the sequence-to-sequence model, which is the same RNN being used, then came encoder-decoder, then came encoder-decoder with a peek, and then came a new technique called attention. The intuition for attention is when you're doing a summarization of text, when you have a bunch of text, you read the text, and then you're trying to summarize the text. Or when you take a bunch of text and you're doing a language translation. What would normally human beings do? After reading the entire sentence or paragraph, when you're doing the output, once in a while you want to go back and check maybe one or two words or one or two phrases that is of more important for you at that time step, because you're outputting word number 7, but for word number 7 you want to go look at word number 8, 23, 44 of input, because those words are modifying my output number 7. So model is getting a chance to go back and look at what was the input, and instead of looking at the real input, it actually goes and looks at the hidden state at those words. So if each word is a time step, so instead of 7th word and 10th word and 25th word, at time step 7, time step 14 and whatever, 24, look at the hidden states. I want to look at those hidden states and predict my YT at this time. That is attention. So it's instead of only looking at the last hidden state of the encoder, I want to go back and look at specifically a few hidden states of the encoder when I'm doing my decoding activity. Okay, that's a mathematical implementation right there. There's another way of showing attention, which is exactly the same again. You have an encoder. In this case, you have a multi-layer encoder and with also skip-level connections. This is from this paper. Is the paper? Yeah, paper is right here. You guys can check. All my details are from papers, so you can actually go back and check. When I share the slides, you will also have the references to the papers. And you have, this is the decoder happening here, and the decoder at every time step, it actually goes back and looks at the hidden state, the output hidden state of the encoder, but also it goes back and checks what were the hidden states of various, the hidden states of encoder at various time steps. Okay, we talked about so much of hidden states, encoders, decoders, having a peak, attention. This all looks extremely complicated programming activity. It's not. I think this is Keras model. Yeah, Keras. Almost every framework has some way of implementation of it. All that you have to do is, for example, this is a very simple sequence-to-sequence implementation. And in a sequence-to-sequence with peak, I think you just have to set the, I can't see from, yeah. Peak is equal to true, I think. Yeah, peak is equal to true. That's it. The model will look at when you say peak is equal to true, it constantly goes back and checks the hidden state of encoder for every time step of decoding, and with just that one. So the programming aspect is very, very trivial. So if you guys are not able to do the hands-on today, right now, in the morning, when we started in the morning, or if you're not able to, if you think it's too complicated, that is becoming more and more trivial. But it's the concepts people, I think, need to be aware of. Let's talk about word vectors, so how to create vectors out of the words. Before I get into words, let me define a concept called vocabulary. If you, for any NLP cases, you have an input corpora or a text that goes in, you need to identify how many are unique words in my input corpora. That's called vocab, the vocabulary. And the vocabulary size is an extremely important factor at this point of time, because for encoding purposes, you need to have a set of vocabulary where the encoder takes those words from the vocab, and while decoding, the RNN or LSTM also needs to pick from words from a vocab. They can be two different vocabs, different set of vocabs for encoder and decoder, but the size of a vocab at this point of time, I have not seen more between, actually I've seen between 50 to 80,000 words. I have not seen enough experiments where the vocab size is more than that. What does that mean? It means when you're doing a language translation from English to French, the different types of word the model can understand is those 50,000 or 80,000 words. If you give a new word, it doesn't have a clue what it is. And it puts out something called UNK, unknown, U-N-K, because it has not been trained on this new word which you are giving during inference, because while training, it's not in the vocab, and hence it doesn't know what the word is. Similarly, when it's doing decoding, doing training, it picks up the words from its own vocab. But if it encounters some strange word, and it does not know what the meaning of that, and if it's not there in its decoder vocab, it again outputs an UNK there, because it does not know. So you need to have a vocab. Why can't we have 1 million as a word? Computationally expensive, because you need to have that amount of data set to which you are using 1 million tokens and as inputs and another 1 million tokens as output, which is not possible. So 50 to 80,000 is what it is. So with that definition of vocab, one-hot vectors is the most common one. Many times this works even better than word-to-vec, but a lot of people actually believe word-to-vec also work. I do have an experience of training my question answering model using all the three models, one-hot vector, word-to-vec, and glove. I found the model accuracy was the highest, 72% when I was doing one-hot vectors. But a lot of people feel one-hot vector does not capture a few essential information. But let me first define what a one-hot vector is. Let's say your vocab is 10 words. I am going to the movies. If that's your entire corpora, so you have a 7-word vocabulary. Okay? Let's say you have a 7-word vocabulary. You create a vector of 7 dimensions, that is 7 zeros, but the vector for I will have a 1 in the first place. So there will be 1, 0, 0, 0, 0, 0, 0. So if you have 7 words, and if you're giving a vector for word I, and I is number 1 position in your vocab, you put a 1 in place of 0 for that vector, and that becomes a unique identifier for that word, and same is the case for the rest of the words. So one hot vector is, or 1 of k, one hot vector is the vector with lots of, or actually everything zeros except 1 at that place where the word is in the vocabulary. Okay, that's a one hot vector. But the problem in that is, I am going to the movies, movies I am going, I am the to movies the going. If you rearrange the words in any fashion, the word to one hot vectors will almost have a similar the vectors, and it's not capturing the sequence information, which is the biggest drawback in one hot vectors. But I've seen one hot vectors working very effectively too. So you may want to be aware of how one hot vectors are created. Another way of creating word vectors is co-occurrence vectors. If the word I am, if the word am comes almost many times next to I, not next to movies, am movies, the word am does not appear next to movies, but mostly occurs next to I, you want to capture that message, that information. So it's called co-occurrence metrics. Is you want to identify, you want to give vectors to words, similar vectors to words which occur very close to each other. So there's a style of doing it where if this is the entire vocabulary, I enjoy flying, I like NLP, I like deep learning, you actually make a table, you find for each of the word how many times the word occurs in next to it, and then you can put the numbers. I don't want to get into the details. I have not seen people using co-occurrence vectors. Actually, I have not seen ever in the last 2-3 years papers people using it. But I just wanted to share that method of doing it. Word to vec is the most popular, and there's another method called glove, which I don't think we'll be talking, but word to vec is another way of doing it. It does actually do it in 2 different ways. One is continuous bag of words. There's another called skipgram. Continuous bag of word is you create a vector based on large amount of corpora where you pick a word and you predict the probability of 2 words before and 2 words after using continuous bag of words. That's a skipgram. Continuous bag of words, you actually identify 4 words, 2 words before and 2 words after, and then you predict what the word is. But you don't need to do any of the math. There is in many other frameworks like TensorFlow, for example, just a one-line code where you want to create word vectors for a bunch of corpora you have. You can just run a couple of lines code and then you can create word vectors there. So let's create word vectors. Okay, I need to restart it again, I guess.
Excuse me. This side.
This side.
On your left.
On my left, okay? Okay, yeah, there you go.
Okay. I was just confused by the fact, as you mentioned, that glove is another representation of word vectors, or is just a pre-trained model that you can use out of box?
Glove, when you expand it, it's actually called global vectors. That's another way of doing vectors, identifying vectors. Word to vec, glove is actually invented by Google. That's a way of creating vectors. And word to vec is another way of creating vectors.
Is there a fundamental difference in how they create it?
As far as I know, I think word to vec using continuous bag of words and glove is using skipgram, but I'm not very sure.
I think a glove is a content-based model, and word to vec is a predictive-based model.
Word to vec is a very good model. Yes, I agree. What was the first one you said?
The glove is a count-based model. It's a concurrency matrix. And the word to vec use like skipgram and those 2 models.
Yeah.
So they are different. Essentially, they're
You may be right. I don't know about much glove because I never used glove. I only use word to vec. Yeah.
Okay.
I thought it's glove is uses the skipgram model to identify vectors, and word to vec I thought it was continuous bag of words, but I may be wrong. Okay. So if you can open the word to vec file, and it's actually a default code that's available in TensorFlow. I picked it up. I want to show you the fun thing in that. Some people may or may not know it. Okay. So it runs and then of course exits. If you're running it on your machine, go back to your folder wherever you're running it. There is a file called, okay, it's doing it right now. You see, I think it's learning. Let me see if I can. No, I can't increase the font size here, so you have to see. It's at the end of each epoch, each training round, it's picking some random words and then identifying what words occur closer to this word or which seem to be similar. Initially, for the first few rounds, it is very inaccurate, but as you go deeper into the training towards the later part, if it picks a word, let's say Washington, it picks up capital cities of other countries, which it found based on the text. I think it's Wikipedia text it's looking at. If you can run it on your machine, you can keep on looking at it, but I'll wait for it to run. I think it takes 5-10 seconds. I think I've already run it once, so I'll show you. There's a file that ends up creating called tsni.png. This is the image of file that gets created of all the words. Actually, you can see based on the corpora you're training this on, model will create vectors for each of the word, and when you post those vectors onto some sort of a vector space and you look at them, it's a n-dimensional image, but you're looking at it as a 2-dimensional image. When you look at that, words that occur frequently together would also appear in the image together, showing that the vector the vector you are creating, or the vector you are assigning to a word also is similar. In other words, I think they're capturing the essence of similar words have similar vectors and they co-occur, they appear closer. So let me see if I can give a specific example. I think with the text, like you have the European, Chinese, some countries there, German, but then I think it becomes English also. So you have, it's French, it's picking up languages there. So when you run this on your computer and you can see this file, this is called word embeddings, which is a pictorial representation of how the vectors look when you put them onto a 2-dimensional image, multidimensional in this case, to show that vectors are actually capturing the essence of which words are closer to each other. Okay, so let's get to this is a non-NLP solution, so I'm actually going to skip that and I'm going to go to magic of language translation. I'm actually going to tell you how to design a model that's going to do language translation. I'll talk about various building blocks on that. Yes, you had a question? Yeah, tsni is an approach which actually reduces dimensionality just so that you can show it in a 2-dimensional, but it's actually a multi-dimensional. It could be 200 or 300 dimensional. Oh, sorry. So sorry. Then ask me the question again. Sorry. One hot vector, yes, the dimensionality you cannot change because the dimensionality of each vector in a one hot vector method is the size of the vocab. In word2vec, yes, you can define the dimensionality. It can be 200, 300, 500. Typically, that's the number people use, 200 to 500 as a dimensionality of vectors. Okay, let's talk about machine translation if you're trying to use. So you will use sequence to sequence, and then more than sequence to sequence, you can use a decoder, encoder-decoder, and you can add attention on top of it. Now let me talk about how do you add a language model to it. So you actually have a sequence to sequence model. Let me define what a language model is. Language model, in a very, very simple term, is how to predict what the next word is given a few input words or the previous words. In other words, let's say you give an incomplete sentence to the model. It will predict what the next word would be. Or if you give a wrong sentence or a correct sentence, it actually gives you a probability of how right or how wrong the sentence is. So in other words, it's actually like a human being looking at the incomplete sentence. It will start predicting what the next word may be. The cat sat on the mat, if that's the sentence, the cat sat on, it'll be, the next word will be the, and after the it could be mat or a table or a chair. It predicts based on the training what the model has got. So language model is a single RNN on LSTM which reads, let's say Wikipedia. Many language models are trained on Wikipedia. It takes one word by one word and it makes a prediction at the end of the word, but it knows what the word is, so it takes the input as the correct answer and does the back propagation and then does the loss computation and back propagation. In other words, it's actually trying to assimilate what's in Wikipedia. Let's say if they have 3 million articles in Wikipedia, it actually reads the entire 3 million articles, and now it is intelligent enough to see how a sentence or a paragraph is written in Wikipedia. And because Wikipedia is generic enough for human communications, because it has articles on science and maths and technology and travel and tourism, whatever, it has been exposed to so many types of sentences. It is a model well-versed in English language. So you can give an incomplete sentence, it predicts what the next word is. So that's a language model. So when you do a machine translation, and if you do an encoder and decoder, what is happening is, after you give the inputs, the model takes the hidden vector, the context vector. So you have the ST is the hidden state of translation model. TM is translation model. So you have a translation model which you have trained already, which is getting creating its own hidden state. And in normal situation without a language model, what you would do is you use just this ST of TM to start making your predictions of YT, because that's what the YT you're trying to predict. But because the YT could be wrong, and to enhance the accuracy of prediction, before it predicts YT, it wants to use the hidden state of a language model too. So you're actually taking the help of a language model, and it says, hang on, as a translation model, I think the next word is the cat sat on his table, on my table, on it table. It makes, let's say it makes 3 predictions, seems to be high probability, it and him and is. A language model will look at those 3 top predictions, top K predictions, and then says, you know what, out of those 3 predictions, Mr. Language Model, translation model, I think the right word there should be on the or on his, whatever. It corrects the predictions given by the translation model. So let me explain again. So based on the translation model, you have a hidden state coming in. You also have a language model hidden state coming in. You combine the two mathematically. Of course, there's an attention mechanism here, and it uses the essence of a language model and a translation model to make the final prediction. And people have found this to have a higher accuracy. This is actually from a paper. It's published here. So they actually have 2 different models. You actually have a shallow integration and you have a deep integration. I won't go into the deep integration, but the essence in this paper is for a regular translation model, instead of just using the encoder and decoder, if you combine a language model along with that to the encoder-decoder, the accuracy of your translation goes up. There's another paper that came later. One of the biggest problems in translation is unknown words. Even though you have a 50,000 or 80,000 as your input tokens or input vocab, and another 50,000, 80,000 overlapping or not, vocab for the output vocab, the vocab for the output RNN, sometimes the model does not know what is the right word for this translation. 2 years ago, 3 years ago, models were trained, if you don't know what the word is, put an unk there. But obviously the quality of translation is not really high, so they have to figure out how to eliminate the unk. So one idea was, let's add a language model, which I just showed you in the previous slide. So adding a language model eliminates the possibility of unk, because if the translation model cannot figure out, the language model may be able to give you a few ideas. But even then, you still have unks. So the next idea was, during training, so you have a language translation training from English to French, and etc. You have a million sentences and connecting another million sentences. While doing the training, the model actually creates a dictionary called alignment dictionary using attention model. Why? While translating this word, when I'm outputting this word, I knew using attention I had to focus on this word. So maybe the translation of this word is this word. So I'm actually having a one-to-one mapping, so I'm creating an alignment dictionary. So so it creates an alignment dictionary during training, and when the training is done, when you're doing the inference, if you find an unk, even after using a language model, it goes and checks the alignment dictionary and say, okay, hang on, I don't know the translated word in the target language, but at least I know what was the word which I was translating it from. So I'm actually going to just put the source word right there. At least you have a sentence which is not dramatically wrong, and if you know hopefully the source language too, you'll be able to figure out. That was a step further to improve the accuracy of, so eliminating unks. So creating a word alignments was the other one. There's another technique people have used, that's a little more complicated. Let's say you have a corpora in source language and corpora in the target language, and you want to create a model that takes source and outputs in the target language. But if I have only 1 million sentences, how can I expand the sentences more so that I can have a smarter model? So they found first, okay, do I have a different set of target to source? I take a target corpora and convert that into a source language, attach a language model for that to bring it higher accuracy. Now you have an additional corpora of your source language, and you can use that new source language and the original source language together as a bigger corpora, and you can train the model on that. So that was another model people have created called maximum mutual information in this paper. You can read that. So those are two techniques to improve the accuracy of translation. There's another technique. Let's say the model is translating the sentence, and the translated sentence till now is, I went to, and it has to predict the next word. Typically, prediction means the model is giving a probability number for each of the word in your vocab. That's what it means. And it's making a softmax predictions. But whatever is the right word, the probability is 0.99 or whatever, but the words which definitely not possible, it gives a probability of 0.001, 0.1, whatever. It gives low probability. So by picking the right threshold of your probabilities, you can pick the top word, and that's how prediction happens. But some people said, I went to, if the next word is the, it can be the, or it could be I went to, I don't know, let's say a different, I went to, what is that? I went to the conference. Now, instead of the, let's say I went to the movie, conference, play, and a game. Yeah, let's say those were the top 4 probabilities that came in. Of course, I went to the conference was the top probability, but the probability was 0.993, and the next probability was 0.992. Sometimes, just because something is the highest probability, you can't just take that. So they figured out, in a greedy search, the model doesn't care for what was the second probability word and how close was the probability to the top probability. Even if the top probability is a very, very minute change, it just takes that as the answer. That's called greedy search. It looks for the words in my vocab, decode vocab, with the highest probability, and I'll just take that. Whereas some people suggested, no, that's not going to work. I'm actually going to take the probability of the first word, like I, and then when I predict the second word, I compute a dot product of the probability I went, and when I make the third word, I went to, I'm actually doing a probability of the unigram, bigram, trigram, all the words before I'm done with the sentence. So mathematically, how expensive this computation is. Let's say the first word, when you're making a prediction, and if your vocab size is n, you have n predictions. Okay, you take all the n predictions, and when you make the second word prediction, you have n predictions there too. But in full search, what you're going to do is you pick every word in the first prediction and find out the n predictions that come next to it and do a probability of the bigram. So you take the first word and then go the first word, second word, third word, fourth word, all the way to n. Take the second word, then again first word, second word, third word, all the way to n. Third word. You're having a n times n computation. And if it goes to the third word, then you talk about n times 3. That's a computationally expensive search. It's called full search. People said that's not going to work, so they actually came out with a new technique called a beam search. You take the top k words, you don't like top 3, top 5 words, and you keep the top 5, and when you make the next prediction, you compare against those 5 words, not the entire n words. So it'll be 5n. So for each of the word you have n predictions, you have 5n. It's not n squared, but it's just a 5n, which is actually a lot cheaper. So beam search is a suggestion that is made when you're doing a language translation. So instead of picking the top probability, you go for the next, you take the top 5, top n, top k actually they call it. And there is another paper which came out where to increase the diversity, you actually can force some random rewards. You just give a random reward for the prediction, the probability prediction at each step. There are more tricks on how to get more data. I think I mentioned this. You actually you have a target to source, you do a conversion, and using a language model of the target language, you further process it to get extra corpora. I mentioned this already, but that's another way of increasing the accuracy because you have more data with you. This is the best paper if you really want to get into language translation. You want to read this. This is the Google paper which was published in 2016 December, I think, so hardly 8-10 months ago. This is the model they're using for the translation in the production stage. So if you're using a Google app for translation, this is the paper that's based on. They actually use lots of improvement techniques in this. For example, the encoder and decoder are multi-layer. It's 8-layer RNNs. And the encoder, at least in the first layer, is a bidirectional. What is a bidirectional RNN? Let's say there is a sentence called, I am going to the movies. And RNN, in unidirectional RNN, takes the first word I as the first time step, and the second word in second time step, and third word as third time step. In a bidirectional, you have two RNNs. One is taking the sentence from left to right, and the other one is taking from right to left. So at any point of time, the hidden state of, let's say if you combine the hidden states of both the RNNs at every time step, that hidden state will not only have what was given as input in the past, it also knows what is going to come in the future, because the reverse directional RNN, which already has looked at the last words, and it has given that information to the hidden state. So you actually have the advantage of that. So you have a bidirectional RNN on the bottom layer. You also have a skip level connections where you are passing on the information of hidden states, which improve the accuracy and reduce the computational power, residual connections they call it. They did a beam search. Another problem of translation is you eliminated unks, but there's another problem called repetition of words. If the model does not know that I've already used this word for a same context, for a same meaning, it just may repeat the same word and same meaning again. Sometimes you find translation models or even summarization models repeating repeating the words. To eliminate the repetition of words, there is something called coverage penalty. While translating, while outputting a word, if you go back and look at using attention, if you go and looking at word number 7 and 8, and if you think I've already looked at word 7 and 8, that means I'm already got the essence out of the word, but I'm going back again, so I won't do the translation there. I do a coverage penalty. If I've already covered certain words in my input corpora, I won't do it again. That's called coverage penalty. So that eliminates repetition of words. Also for computation, low precision numbers, if you're using a 32-bit or a 16-bit computation, the mathematics you're using to compute your probabilities it's really high, computationally high. They found when you bring down the precision arithmetic to even 8-digit and 4-digit numbers, it lost hardly any accuracy. So, but that improved tremendously the computation time. Also, they identified some rare words. I think maybe in the other paper they have, when you put an unk, let's say you don't know what the meaning of the word is and you put an unk, but unk in the first sentence, unk in a third sentence, and unk in a seventh sentence looks like same because you put in the same unk, but they actually are referring to different words. So they found an alignment technique where even though they're putting an unk there, they're referring to the word which is triggering the unk, which gives a better understanding for a human being who's consuming the translation one. Also, they address the rare words in a different way. Let's say you have a sentence called a word called running, and the model could not find an appropriate translation of that. What it does is it actually goes and look at what was the word using attention and starts breaking the word into smaller pieces. It does maybe lemmatizes and stemmatizes, or it picks up a few characters. So if his running is the word it could not understand, it says, can I understand the word R? No, it doesn't make sense. RU? No, it doesn't make sense. RUN? Yeah, it makes sense. So I'm actually going to pick piece of that word, translate, and highlight it. It's an incomplete translation, but at least instead of running, I found a word which is run, and I translated the word to this target language. So that's another way of identifying some rare words, where they start breaking the words into small pieces. This is an overall picture of the model. You can see on the left side multi-layer encoder. You actually have a skip level connections or residual connections. You actually have they're using LSTMs here, and attention is in the middle in the blue box, and then on the right side is the decoder, and there's a softmax blue top horizontal bar on the top, which is making a predictions on the probability prediction of the entire vocab, giving obviously the high probability for the right word and low probability of the wrong word.